This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion on a fascinating paper from arXiv, VerifyLLM, LLM-based pre-execution task plan verification for robots. This paper tackles a critical challenge in robotics, ensuring the reliability of robot task plans before execution. What are the core limitations of traditional approaches to robot task plan verification that this paper addresses?
Traditional methods, often based on PDDL, Planning Domain Definition Language, and formal methods like model checking, struggle with the nuances of real-world scenarios. They lack the common-sense reasoning capabilities needed to handle unexpected situations or implicit constraints. Furthermore, scaling these methods to complex tasks is computationally expensive. VerifyLLM aims to overcome these limitations by leveraging the power of large language models, LLMs, for contextual understanding and reasoning.
The paper mentions that current LLM-based approaches primarily focus on generating plans, not verifying them. How does VerifyLLM differ, and what is its unique contribution to the field?
Most LLM-based planning research concentrates on generating plans from natural language instructions. VerifyLLM takes a different approach. It verifies pre-generated plans, ensuring their logical consistency and completeness before execution. Its key contribution is the integration of LLMs with linear temporal logic, LTL, a formal language for specifying temporal relationships and constraints. This combination allows for a more robust and comprehensive verification process.
Can you elaborate on the role of LTL in VerifyLLM? Why is it crucial for this task?
LTL provides a formal framework for representing the temporal dependencies and logical constraints within a robot task plan. The LLM translates the natural language task description into an LTL formula, which then serves as a formal specification against which the action sequence is verified. This formal representation ensures that the verification process is not solely reliant on the LLM's potentially unpredictable interpretations.
The paper describes a two-step process, translation to LTL, and then verification using the LLM. Can you walk us through the architecture of the VerifyLLM system?
First, the natural language task description is translated into an LTL formula using an LLM with few-shot prompting. This formula captures the temporal and logical aspects of the task. Second, the verification module analyzes the action sequence using a sliding window approach. The LLM, guided by the LTL formula, examines each action within its context, identifying potential issues like missing prerequisites, redundant actions, or incorrect action ordering.
The paper highlights three main types of plan inconsistencies that VerifyLLM addresses. Can you detail these and provide examples?
The three types are: 1. Position errors. Actions are in the wrong order throughout trying to pour water into the cup before heating the water. 2. Missing prerequisites. Necessary actions are omitted, e.g. forgetting to add tea leaves before pouring hot water. 3. Redundant actions. Unnecessary actions are included, whereas repeating the action of pouring tea twice. VerifyLLM identifies these inconsistencies and suggests corrections.
The paper uses two datasets, Alfred LTL and Virtual Home LTL. What is the significance of these datasets for evaluating VerifyLLM?
These datasets are crucial because they provide a benchmark for evaluating the system's performance on realistic household tasks. They are annotated with LTL specifications, allowing for a rigorous assessment of the accuracy and effectiveness of the LTL translation and verification modules. The use of established datasets ensures reproducibility and allows for comparison with other approaches.
The experimental results section presents several key findings. What were the most significant improvements observed after applying VerifyLLM?
The most significant improvements were observed in the reduction of ordering errors and an increase in the longest common subsequence, LCS, similarity between the original and verified plans. This indicates that VerifyLLM effectively corrects the sequence of actions, bringing them closer to the optimal plan. The reduction in extra actions also demonstrates the system's ability to eliminate unnecessary steps.
The paper also includes ablation studies. What insights did these studies provide regarding the importance of the LTL translation and LLM verification components?
The ablation studies showed that while the LTL translation module contributes to the system's performance, the LLM verification component is absolutely crucial. Removing the LLM verification led to a dramatic decrease in plan quality, highlighting the importance of the LLM's reasoning capabilities in identifying and correcting inconsistencies.
The choice of LLM seems to significantly impact performance. What were the observations regarding the use of different LLMs?
The experiments showed that larger language models, such as Claude and Llama 3.2/3b, significantly outperformed smaller models. This is likely due to their increased capacity to handle the complexity of the prompts and understand the nuanced relationships between actions and temporal constraints. Smaller models struggled with the intricate, nested vocabulary required for comprehensive plan analysis.
The paper mentions a sliding window approach for context analysis. How was the optimal window size determined?
The optimal window size was determined through experimentation. A window size of 5 actions yielded the best F1 score, indicating that this size provides a good balance between capturing sufficient contextual information and avoiding excessive complexity or irrelevant details.
What are the limitations of Verify LLM and what are the directions for future research?
Current limitations include challenges with complex temporal dependencies and parallel task sequences. The system also needs improved mechanisms for mapping between robot capabilities and generated plans. Future work will focus on addressing these limitations, expanding to more complex domains, and potentially incorporating more sophisticated reasoning techniques.
The paper concludes by highlighting the potential of Verify LLM to improve the reliability and efficiency of robot task planning. What is the broader impact of this research on the field of robotics?
VerifyLLM represents a significant step towards more reliable and robust autonomous systems. By providing a mechanism for pre-execution verification, it reduces the risk of errors during task execution, leading to improved efficiency and safety. This is particularly important for applications where robot failures can have significant consequences.
This has been a very insightful discussion on Verify LLM. Thank you for sharing your expertise.